together. Now when I say integrate, there I'm talking about a plug flow reactor. In a CSTR, things get a little easier because it's just algebraic equations, but again, you have to solve them together rather than sequentially. Okay, so let me just remind you, these RA equations, usually, as we had in the beginning of the semester, they're usually sums of terms where each term is a rate constant times some concentrations to some powers. Remember that? But when we talk about non-isothermal systems, RA usually looks like, we used to talk about RA as just being the sum of terms that look like KI's times the product of concentrations, Cj to the alpha j. So where the alpha j's are the stoichiometric coefficients on the left side of any reaction arrow. So these should be alpha ji, where I is the reaction. So I am summing over all the reactions, and j I'm summing over all the species. Multiplying by, I am taking the continued product over all the species. Now, until now, when we were dealing with isothermal systems, these were just constants, and these were concentrations to powers. And hopefully, in the simple cases we've been doing in this class, I could write all the CJs in terms of just one XA. Again, in general, in real systems, you're rarely that lucky that you can write all the concentrations in terms of one of the concentrations. So usually you need a differential equation for each concentration. But once you get to non-isothermal systems, these are no longer constants. These are now prefactors times e to the minus EI over RT times the product of concentrations, species, Cj to the alpha ji, where alpha ji is the stoichiometric coefficient of species J in reaction I. Okay, the whole point here is that I'm making with this these equations is that now I have temperature dependence here, as well as from the energy equation, I'm going to have the temperature dependence in here because it's going to relate the C's to T. So I have a temperature dependence in here and in here. And they're often fighting each other. So I want you to be aware they can fight each other. Here, as T goes up, the exponential goes up. This is a minus here, and this is on the denominator. As T goes up, the exponential goes up. Here, as T goes up, depending on the heat balance, C could go up or down. Moreover, I have a bunch of terms here, and some of them can have pluses and some of them can have minuses. So what I left out here was this is some of them can be plus and minus because the stoichiometric coefficient on the product side minus the reactant side of each reaction may be different for species A. It could be positive for some reactions, negative for others. So for example, if if I have a reaction, A plus B goes to 2A, then for the forward reaction, beta for A is 2, and alpha for A is 1 for the forward reaction. For the reverse, so 2 minus 1 is 1. For the reverse reaction, it's the opposite. Alpha is 2, beta is 1. So 1 minus 2 is minus 1. Sometimes it's plus, sometimes it's minus. Sometimes a reaction produces A, sometimes it destroys A. So because I can have temperature affecting this and this in different ways, and I have a bunch of terms, I have to be very careful. I can't just make some general statement. Each case I have to look at individually. Okay, so before we go into a detailed analysis, what I would like to do is try to get us some intuition as to what's going on. So why don't we try to get a little bit of intuition? And in order to get some intuition of the heat balance, or the mass balance and the heat balance, what I'd like to do is I'd like to make the following plots. I would like to plot XA versus T. And I would like to do this for 3 separate situations. I would like to do it for an irreversible reaction, a reversible endothermic, and a reversible exothermic reaction. What I'd like to do is I'd like to plot the rate equation. So what I'm plotting here is the rate equation. Total rates. Okay, if I have an irreversible reaction, totally irreversible. So here I'm not talking about time. Well, at equilibrium, I'm going to reach at infinite time. So what is the equilibrium conversion if I have an irreversible reaction? Then what is the equilibrium conversion at any temperature? 1. So the equilibrium I'm going to write in blue. If I have a reversible endothermic reaction, we learned something. What we learned is that as the temperature goes up, if I have an endothermic reaction, then the temperature goes up, K goes up. So if K goes up, then and A is a reactant, then what happens to the conversion of A?
It increases.
It increases. So what is the equilibrium curve going to look like for a reversible endothermic reaction? It's going to go up. It's going to start low and go up. And eventually probably get towards 1. Because as temperature goes up, the equilibrium goes up. How about a reversible exothermic reaction? It's going to go down. Okay, let's now plot the rates. We know, now this is when when I'm not at equilibrium. Equilibrium is infinite time. For finite time, I have to worry about rates. We know for an irreversible reaction that the higher the temperature, does the reaction get faster or slower? Goes faster. So we know that as I move in this direction, I should go to higher and higher rates. Okay. So now I would like to plot lines of constant rate. So I want to plot lines of constant rate. Do I have a higher rate when I have a high XA or a low XA? When I have a high XA, I have much less reactant. So is the rate going to be higher or lower? Lower. So we expect up here to have low rates because XA is high. However, and at high XA, a high temperature, we expect to have high rates. So these are the highest rates, high temperature, low XA, the lowest rates. So you can imagine the curves, if I'm going from low rates to high rates, go in this direction. Yes? I'm not even talking greater than 0. greater than 0.
So how are you drawing
I didn't draw anything yet.
rates in the XA graph? I mean,
I'm going to draw lines of constant rate. I haven't drawn them yet, so before you ask me how I draw them, wait till I draw them. Okay? Then you could ask me how. I could just draw them because I solved the equations, but I wanted them to be intuitive. So the lines of low rates are going to be in this region, the lines of high rates are going to be in this region. So I think from this point you can kind of see that the curves have to look like this. Where this is the direction of increasing rate. Obviously, equilibrium, there's 0 rate. Nothing's changing. So this, all the low rate curve have to get close to the equilibrium line, and the highest rates are down here. Now the same thing is going to apply in the reversible. Does that answer your question?
I'm a little confused how you
Only a little?
how you put the rates in the XA, because the rate depends on XA.
The rate depends on XA and T. I'm plotting R as a function of XA and T. So I have XA versus T, and I'm plotting lines of constant rate. Because the rate for a given XA and a given T, I have an RA. That's exactly what that says. You had your hand up? You had your hand up? You had your hand in the air. Were you just stretching? Good. Just do Pilates. Okay. The same logic applies to reversible endothermic reactions. Again, the closer I get to equilibrium, the lower the rates. So this way is going to lower rates, this way is going to raise rates. So I'm limited by equilibrium, so that means that the curves have to sort of look something like this. Again, this is the direction of increasing rate. How about reversible exothermic reactions? I want to do the same thing. That is, as I move in this direction, the rates should go up. I mean, that's general, whether it's exothermic or endothermic, the rates should go up in this direction. But the equilibrium curve is a bit of a constraint. So that tells me around here, so around here I'm going to have some curves that look like this. And again, this is the direction of increasing rate. Because as I go down, I have more reactant. As I go up, I have less reactant. So clearly this is the direction of increasing rate. Yes?
in the XA you get in both situations the maximum XA you can get, right? At the equilibrium line, that's the maximum you can get.
Yes, that's what equilibrium means. I can't go across this line. It's like a double yellow line on the street. You get a ticket.
But you can start from the other side.
Sure I can. Then if I start from the other side, then essentially I'm switching these curves back and forth. So if I start from the other side, then usually I choose something on the other side of the reaction as my limiting reactant. Because the reactants become the products and the products become the reactants. Okay. Now, eventually, the slow rate curve always kind of wants, is eventually going to start hugging the equilibrium curve. When the slow rate curve hugs the equilibrium curve, instead of being flat here or going up here, it has to turn around and start going down. Because it can't go past the equilibrium curve. So I follow all these curves. Okay, so now we want to use our great powers of intuition that we've developed because we're chemical engineers with a suit with a little S on it. And we want to figure out what, if we could have our druthers, that is our dream temperature profile. We want to come up with our dream temperature profile. The one thing you need to note is that typically there's a certain temperature beyond which, normally you would say, great, let's go to high temp. For this case, you'd say you go to high temperature. The higher the temperature, the better. So increase the rates. The problem is usually above a certain temperature, you can have materials problems. So either the electronics stop working, or the reaction mixture will corrode the reaction vessel, or something's not going to work. Usually you have a limitation that there's a maximum temperature that's allowable. So let's call that Tmax. I'm going to draw that in all of this. Tmax. Let's say Tmax is here. Okay, so now what I'd like to do is I'd like to figure out, if I have a given Tmax, what is the best possible, the dream temperature profile that I could get for an irreversible reaction. I usually want the highest possible rate because that will give me the fastest reaction I could get for any given conversion, and that will give me the smallest reactor, or if you like, the most product for a given size reactor. So for the irreversible reaction, what's the dream temperature profile? Volunteer? Volunteer means raise your hand, doesn't mean talk out loud. A horizontal line. So that.
At Tmax, we have horizontal lines for your
Okay.
So.
Wait. Let me repeat the question. The dream temperature profile means I'm dreaming, and I'm saying I want this to be a dream, not a nightmare. And for each XA, I want to know what temperature I could have if in the best possible world. So I want a curve, one curve, not 100 curves. You're giving me 100 curves. One curve for the temperature as a function of XA. Or temperature, if you like, as a function of time. A vertical line where? Vertical line at Tmax. So here I get a vertical line at Tmax, because since it's an irreversible reaction, it would be great to have that to be my temperature profile. So at every XA, I always have the best possible temperature, the fastest rate. Because if I went anywhere to the right, of course I'd be too hot. And if I went to the left, I'd go from a high rate curve to a lower rate curve. Well, let's just think for a second the complications. If I had an exothermic reaction here, and I start at Tmax, if the reaction were exothermic, and I didn't do anything, I didn't take any precautions, what would happen as the reaction proceeds?
Temperature would increase.
Temperature would increase. Is that a good thing or a bad thing? That's a bad thing because I go past the maximum temperature. So what do you think I'm going to have to do if I have an exothermic reaction to make sure I don't get fire?
Take the heat out. Take the heat out.
Suck heat out. I'm going to need cooling. Let's say I have an endothermic reaction. What happens as the reaction proceeds? Someone raise their hand.
Temperature drops.
Temperature drops. If the temperature starts to drop, am I at my dream temperature profile anymore? So if I want to get to my dream temperature profile, what do I need to do? Heat it up. I need to heat it up. Okay, so those are some considerations. Let's now go to the reversible endothermic reaction. What's my dream temperature profile here? Someone else who has an answer.
It's again Tmax.
Again, we want to stay at Tmax for the same reason we had it before. We are always the maximum rates. If I go to the right, I'm too hot. If I go to the left, I'm going to slower reaction rates. So I'm moving to slower reaction rates. Okay, now's the most interesting one. Let's say, and this here I'm going to look for someone who has their head buried in their book to make sure I don't call on them. So I'm going to call on those people. Reversible exothermic reaction. What would the dream temperature profile be for the reversible exothermic reaction? The maximum of what?
Of the reaction. The XA.
XA. Here's XA, here's T.
It's going to be in between Tmax and that.
Between Tmax
and temperature that is.
This is just labeling the axis.
No, like.
Take a deep breath and you do a full sentence.
It's going to be where the reaction rate is at a max.
The reaction rate is at a max. I'm not sure what that means. So which reaction rate? I have a lot of constant rate curves. Which one? I see lots of maxes.
The toppest one.
The toppest one. I didn't know that was an English word. The toppest one. The toppest one is a very slow rate. Actually, the equilibrium.
Oh, then it's that little.
Then it's the bottomest one.
Yeah.
The bottomest one.
Tmax.
That's one particular x. I want to know what the temperature should be for many x's.
Wouldn't it then not be a line? It would be like this.
You know, what does this mean?
I'd say this kind of rate of reaction is actually increasing. You would have like a line that goes this way.
A line that goes this way? What? Tell me what. Give me some reasoning.
The temperature would decrease.
The temperature would decrease as.
As the rate of reaction decreases.
Or the rate of reaction decreases as the temperature decreases. Keep going.
Yeah, I think it would just be just a line. It would still be at Tmax, but it would be just a line.
What does the line look like? What does it pass through? Passes through the toppest. Let's not use the word toppest. Starts from the maximum temperature of what? Tmax. Draw a line going which way? Like this? Like this? Tell me how to draw it. The highest rate. Here, this the highest rate is here. This is the highest rate. The lowest rate. Here's the lowest rate. Equilibrium. Describe to me how much. The highest curve here. Okay, how do I get from here to here? Exponential decay? A straight line? For each RA, I go through maximum. Let's see if that's a reasonable thing to do. So, first of all, I have more curves here. Where'd the white chalk go? But first I begin by going up at the high, I should use pink, at the highest possible temperature, even though for these rate curves, I'm to the left of their maximum. Again, because if I go to the right, I'm too hot. If I go to the left, I'm going to smaller rates. So up to here, it's the exact same reasoning I had here. But now the question is, what happens beyond here? And a lot of people seem to have intuited what to do, just have a tough time expressing it in English. The toppest, for example. The highest. Okay, but what would happen, and what was going through your minds? What was going through your minds is if I continued going at the highest possible temperature, then I would start going from high rate curves to low rate curves really quickly, and I'd be limited. I wouldn't be able to get past this XA. This XA is pretty low. It's not high enough to get me a promotion. So what I want to do is somehow eventually end up here where I have a high XA. That's what a number of you had the intuition. But how do I get from here to there? Well, the suggestion was I should try to follow the maxima of these curves. Why is that? Well, for any one of these curves, if I'm at the maximum, what happens? If I move either to the left or to the right, I go to a curve of lower rate. That's the reason. If I sit at the maximum for a given XA, then moving to the left or to the right by changing the temperature will take me from this rate curve to a lower rate curve. So that says for any XA, by hugging the locus of the maxima, I'm always at the highest possible rate I can achieve for that XA. And that's why I stay at the locus of the maxima. So I'm going to hug the locus of the maxima. So what that means is I have a decreasing temperature profile. If I have, remember what did we say temperature profile was? If I have CSTR, if I have one plug flow reactor, then T is a function of what?
Z.
Length, Z. If I have a batch reactor, T is a function of what? Time. And if I have n CSTRs in series, T is a function of someone on this side of the room. T is a function of n. So what this tells me is in these two cases, I want to do whatever I can to maintain T being the constant. In this case, I want T to go down in a very prescribed way. If it goes down too fast, I'm at too low rates. If it goes down too slowly, I'm limited by equilibrium. So they're fighting each other in this case, equilibrium limitations. Okay. Time is moving quickly. Okay, so in order to actually examine what happens with exothermic and endothermic reactions, and these particular cases, we need to write a heat balance. We only have like 5 minutes to go, so I can only start the heat balance. I probably won't get through it. So let's do a heat balance. Okay, so, well, the first thing is I have a homework set for you that I still need to photocopy, and that's on multiple reactions. What was the last homework set I gave you? 4. I don't know what 4 is. What topic was it? Oh.
Multiple reactions. Multiple reactions.
Homework number 3. Homework, was that the one with
Yeah, that's the one.
this one?
Yeah.
Okay, did you hand this in yet?
Half of it.
Well, you gotta finish it and hand it all in. Let's see what the next homework is. This is multiple reaction, single reactor. And the next homework is this was homework number 4 or homework number 5?
4.
4. All right, well, I'll photocopy up, yeah, homework number 4. I'll photocopy up another homework. And I'll leave it in my box by the end of the day. Okay. We also, by the way, have another class to make up. Before I start the heat balance, I need this other class. We have 2 more, at least 2 more classes to make up. So, some people are away on Friday. Do we have a time we can make it up before then? Say Wednesday.
Wednesday, 6.
Huh?
Good. That's 6.
How about before 2? When does your class end before then?
That's your class.
Huh?
It's your class.
My class.
So the
Pharmaceutical goes from when to when?
11 to 12:15.
11 to 12:15. How about tomorrow? see. How about Thursday?
We're not.
Huh?
We're leaving Thursday morning. How about Wednesday at 6? I'm sorry.
I'm sorry. Let's see.
Laboratory analysis.
At what time?
Wednesday from 5 to 7:30.
Yeah, but the professor always comes 2 hours late.
It's midterm.
Guess who
Okay. what's that?
that is. Everybody, all the same.
How about Tuesdays?
Tomorrow.
Huh?
Yeah, we could do it
From
tomorrow.
what time to what time? 2 to 6. How about before? So how about Tuesday morning?
We finish at 12, right? 12:30?
Design and process.
Design.
Tuesday at 12.
12:30. Because we designed at 12:15.
Okay, so Tuesday, 12:30 to 2. Okay, so why don't we do it next week, Tuesday at 12:30 to 2? Everyone's going to be back by then? Because for tomorrow, there's too little notice. And that way I also have to get a room. So why don't we have 2 Tuesdays in a row? The next, I just don't want to get too close to finals.
For Tuesday, we'll only be at Steiner. For tomorrow.